Hi again. So this week I am going to briefly discuss the vertical and horizontal motions. Last week I introduced these three equations, and I mentioned that if you have an acceleration that is not a constant, then for example the first equation changes as follows. Instead of writing at, now we have to write a as a function of t dt, and then do an integration going from 0 to t or whatever time to a given time. Now the equations that we are using in both directions, along vertical and horizontal directions, are as follows. Now we mentioned that for horizontal motion it is whatever the given values, acceleration, you can have a given value. If it is decelerating, then of course you have to use a negative acceleration and so forth, right? But when it comes to vertical motion, there are a couple of things that we need to understand, that we have to always use a reference point. So here we have vertical motion, because this was a discussion that we had in the class. I had some students coming over to me to get this clarified. So when we do vertical motion, at least I always take up as my positive direction. This direction, positive y direction, is my positive direction. So this is the reference direction, right, for me and for us in the class. If someone takes downward as the positive direction, of course they can do the work as well. But thinking ahead for projectile motion and all, I decided to stick to this. So up as my positive direction. So when you do that, unless stated otherwise, the acceleration along y direction or along upward direction always stays as a negative value, negative 9.8 meter per second square. We know that it is going against gravity, and when you throw a ball upward direction, it always stops right at some point. So these are the problems that we discussed in the class. So here you have pitcher tossing a ball, and at this point up here you have the velocity equals to y component velocity equals to 0. So here you have an initial velocity vi, and it decelerates at 9.8 meter per second square, and then at the top it stops, and after it stops, the return trip, you can see in the return trip the velocity is increasing, and in a problem like this, the final velocity, if you just take this as the final velocity, the magnitude of the final velocity and the initial velocity, they are equal. The directions of course are different, but the magnitudes are equal because of the symmetricity. And also another thing that I mentioned, like couple of keywords, or I call them magic words. So the keywords that you need to pay attention to when you are doing vertical motion, keywords, let's put it like that. Keywords. So if you see or hear the word falling, dropping, starting from rest, in all these cases, the initial velocity equals to 0. However, if you have a situation where an object is throwing down, then there the initial velocity is not equal to 0. Whether it is whether the object is thrown, or if it is falling or dropping, either way, unless stated otherwise, the acceleration unless stated otherwise, the acceleration along y direction stays as negative 9.8 meter per second square. So this is basically the summary of the vertical motion. Now the same works for the horizontal motion. I mean, in the class we discussed that first, but it's okay. So for horizontal motion, as I mentioned, the same equations will be used, and the keywords starting from rest, that also gives us initial velocity equals to 0. And also sometimes students overlook the fact that the object stopped at the end. For example, the object stopped at the end. Stopping at the end, that tells us that the final velocity of that motion equals to 0. And also, if you have, like, starting with an initial velocity, certain initial velocity, and that definitely we know that initial velocity is not equal to 0 because it is given starting with a certain initial velocity. And then if the object comes to a rest at the end, or if the object stops at the end, then we know the acceleration is negative. Where v finally equals to 0. So the acceleration, you have to expect a negative acceleration here. We are expecting a negative acceleration here, or in other words, it is called a deceleration. It is a deceleration. So just don't be the followers of these equations. Read the problem, understand the problem, and if you see these type of keywords starting from rest, for when initial velocity equals to 0, the object stops at the end, and there you have the final velocity 0. Starting with an initial velocity, that means initial velocity is not 0. If the object stops at the end, I mean, if you just take this as a pair here, starting with a certain initial velocity and then comes to us at the end the object stops, then we know that the object is decelerating. And if you are to plot the graph corresponding to that motion, you will have something like this. Assuming that the deceleration is a constant deceleration, we have v meter per second on the y-axis and the time seconds in the x-axis. So you have something like this: initial velocity over there, final velocity over there, and then we are drawing a straight line here because we take a constant deceleration, a negative, constant and negative slope. Negative slope represents a deceleration, right? So that's how we do it, and I am now going to discuss two problems from each case. Okay, now look at this problem. You can pause the video and read it. A rock is thrown vertically upward from ground level at time t equals to 0. At t equals to 1.5 seconds, it passes the top of a tall tower. And 1 second later, it reaches its maximum height. What is the height of the tower? Now, this is an interesting problem. And what you can do is just draw a little picture. I always encourage you to draw little, a cartoon picture, because that helps a lot. So here we have the building, and this is the maximum point, right? So we have like, you know, the ball is thrown from the ground, and at this point that marks t equals to 1.5 seconds. And then at this point the total time, if you check it out, 1.5 plus 1, so this point you have the elapsed time is 2.5, because from here to here it says the time is 1 second. Read the problem again. And then if you look at these two places, I'm going to mark this point as A, and if you want to mark this point over here as B and the topmost point as C, then we can actually do a couple of things. Now this is a situation where we have like, you know, the gravitational acceleration AY, or the acceleration in the upward direction, equals to negative 9.8 meter per second. So I am going to do two tables. Now table number 1, I am going to take the information given to me from A to B. There's nothing much, right? I'm going to take the initial velocity, which I don't know, and then acceleration I know, negative 9.8, and from A to B the final velocity I don't know, and then the time elapsed I know, 1.5 seconds, and the height of the building again I don't know. Height of the building, which is delta y, I don't know that. And then I am going to take another. Okay, I am going to do the B to C motion now. It's pretty straightforward, right? At the top we have final velocity 0, initial velocity we don't know, acceleration is negative 9.8, and the time is 1 second, and that's pretty much it. What I am going to do is, from B to C motion, I am going to find the initial velocity, and this initial velocity is going to be the final velocity of A to B motion. The initial velocity from B to C, that means the velocity at point B here, right, going up, it is going to be the final velocity from A to B motion, like, you know, here this is going to be the final velocity. So basically these two guys are the same. Now let me do the like, you know, the math quickly, so I won't really exceed this video more than 20 minutes. So from B to C, V final equals V initial plus A T. V final equals to 0. V initial is what we are looking for. A is negative 9.8 and T is 1. So you have VI equals to 9.8 meter per second. And this is our initial velocity for going from B to C. Now I am looking at the table going from A to B, and this A to B motion shows we are looking for the height, right? I called it delta y. Delta y equals to VIT plus 1/2 AT square. And delta y, you can call the height of the building as h if you want, h over here on the table. And then V initial we don't know, time is 1, and then 1/2, A is negative 9.8. Actually, sorry, time is not 1, time is 1.5, right? Yeah. So here you have 1.5, and there you have 1.5 square. So you can find h if you can find the initial velocity. So let me put everything that I have here, and 1.5 square is 2.25. Now finding initial velocity for this segment, I am going to do it separately over here. Finding VI at point A. So you get V initial equals V final plus AT. So I think it is V final here. V final equals Vi. So you have V final on this side, which is 9.8 coming from the previous part from here, and 9.8 equals Vi minus 9.8 times 1.5. So you bring it to the other side, 9.8 plus 9.8 times 1.5, and there you have the initial velocity, and you can find that and take it to the point over here in the first equation and get the final answer. So there you have 24.5 meter per second. Now we are going to substitute it in this equation to find h. So I'm not going to spend too much time here. You guys can do the substitution. H equals 24.5 times 1.5 minus 4.9 times 2.25, and that gives you h. The answer is 25.73 in meters. Okay, so that's it, and I'm going to stop it here.